In this example, I'm going to demonstrate how to draw a C curve and an F curve for a completely mixed flow reactor. And this example is similar to the problem that is posed on homework 3. The fourth problem in that assignment is talking about the same kind of a thing, a completely mixed flow reactor where you're asked to graph a C curve and an F curve. And so this example that I've cooked up is going to illustrate the same principles that you can use to solve that homework problem. The starting point for this solution comes from the notes that were presented in class previously. This is the expression that tells you the concentration of a reactor that's being flushed with a tracer. So this comes from our lecture notes. And so this equation is the one that we're going to be using to show the concentration as a function of time, and it's based on the initial concentration C naught. So we go back down here to the equation. C naught is the original concentration in the reactor. T bar is the hydraulic residence time. Sometimes we use the character theta to refer to that. And then T is just some time that we're interested in for the interval in question. All right, so let's get to this example. The first thing we want to know is the initial amount of the thing that was added, the tracer. And so what we have is 1.5 kilograms. The volume of the reactor, as it's described, oh sorry, no, the 1.5 is from the homework assignment. Here in this example it's 5.0 kilograms. All right, the volume of the reactor in this illustration is 150 cubic meters. And then the next thing we'll take a look at is the flow rate. And the flow rate that's described is 0.25 cubic meters per second. And so with those parameters, we can calculate the initial concentration. And the initial concentration will be the amount that was added divided by the volume of the reactor. And so that gives us the number of kilograms per cubic meter. Right? Let's just double check that yep, kilograms per cubic meter. Now if I want to know milligrams per liter, then I'd need to divide kilograms by 1,000. So let's do that here. C naught is equal to, and we were going to have the units be milligrams per liter. And so it would be, to get kilograms to milligrams, we need to divide by, we need to multiply, because there is 1,000 grams in a kilogram, and then we multiply 1,000 again to get milligrams. But then remember that there's also, if we go from cubic meters into liters, there's a factor of 1,000 there as well. So then we divide by 1,000. So essentially the second 1,000 is just canceling itself out. So 33.33 milligrams per liter is our initial concentration. The other thing we want to know is the hydraulic residence time. How long does it take to fill the reactor? So HRT, sometimes we call it T bar, sometimes we call it theta. If I insert the symbol theta, they all mean the same thing. And so, wow, that's a big equal sign. I'm not sure why I made it so big. I guess ultimately it doesn't matter. Okay, so how long is it taking in seconds to fill up that reactor? Well, then that's just going to be the volume of the reactor divided by the flow rate, and that tells us it's 600 seconds. That's the amount of time the average particle spends inside of the reactor. So what I'm going to do now is set up some columns that I'll use for graphing. I'm going to have time in seconds. I'll have the concentration as a function of time in milligrams per liter. I'm going to set up a column which is the ratio of C to C naught. And remember, the way I'm going to solve for that is with this expression. I'll have the column that's the amount remaining, and then my F curve. All right. So to start off with, like how many seconds, we'll start at 0, and then just to get sort of like a smooth curve, I'm going to have it say like every 100 seconds. And if we need to change that, then it's easy to adjust. So let's just drag this down that far for now. Okay, the concentration initially is this initial concentration, starting things off. And the initial C to C naught, we're going to use this formula. So e to the minus t divided by t bar. E to the power of minus t divided by t bar. All right. So equals E, and in Excel the formula for E is exp, and then we want the ratio of minus t divided by our t bar. And I'm going to press F4 to anchor that so that when I drag down and sideways and so on, it'll always look at that same value of 600. All right, so let's see the concentration now here. Actually, rather than referencing this initial concentration, what I should do is I should say it is this times the original concentration, because that fraction is going to go down. And again, I'm going to anchor this as well. All right, so the concentration after 100 seconds is going to be 84% of the initial concentration. There's no reaction happening here. It's just a tracer that's being flushed out of a reactor. So I can drag that down. We see the concentration is decreasing. So I can drag both of those down just by double-clicking in the edge, or you can click here and drag, or I'm just going to double-click in the edge and it'll carry it through. Now, one of the things that we said in that previous lecture is that at the residence time, 36% remains. So let's double check and see if at 600 seconds, 36% is remaining. And that's what the fraction is saying. So we know we're on the right track. So if we want to make a graph of this now, and that's what it's going to ask for in the homework. In the homework assignment it said make a C curve and an F curve. That's what you need to do. So we're going to come up with a graph. I'll insert a scatter plot like this. It doesn't necessarily have to be that big. Let's add some data. Okay, I'm going to graph the x is going to be time. So we'll drag that down here. And the y values are going to be the concentration as a, we could either do the concentration or the C to C naught. So let's do this. And I'll be sure and label the axes so that it's clear. Let's go up here. Okay, so we're going to call this chart the C curve. And here we want to add axis titles. And so this is our time in seconds. And then here is the C to C naught. So the concentration at some time as a, as a ratio of the original concentration. And I guess we could change it so that it's a line, smooth things out a little bit. That looks nice, right? Okay, so there's our C curve. That part's done. So now what about the amount that's remaining? The amount that's remaining is going to simply be this, this fraction times our original amount. And so how much is in there before anything has been flushed out? It's that times the original amount. And I'm going to anchor that by pressing F4 so that when I drag this down, it's always looking at the original amount. So there's inside the reactor, before it's flushed out, 5 kilograms of this tracer. After 100 seconds, there's 4.23 kilograms of the tracer remaining, and so on. So I can do the thing where I'm dragging it down to, fill the calculations lower. I'll just double click in the edge here. All right, now for the F curve, let's go back to the class notes from the lecture. The F curve formula is here. It's the amount initial minus the amount remaining divided by the initial amount. So F is A naught minus A sub R divided by A naught. Let's go back to the Excel. All right, so here's our A naught. Here's the amount remaining at any given time. So the F at this point is going to be equals the initial amount. I'm anchoring that because I always want it to be that value, minus the amount remaining. I'm not anchoring that because as I drag it down, I want it always to look at the new amount remaining. And I'll put parentheses around this group so that when I divide, I'm dividing by the difference, divided by the initial amount, anchored. All right? So F curve, double click. Now the traditional shape of an F curve, if we go back into the class notes, the traditional shape of the F curve is going to look like this. So let's see if when we graph our data, we get the same thing. Just to make things real easy, what I'm going to do is I'm going to copy. So right click, copy, and I can paste. Paste. And then I'm going to change this to say F curve. And see how when I click down in here to the data, it says time versus C naught. Well, I want it to be time versus F. So I'll just drag this blue box so that it's asking what data should I graph. Now it's going to be graphing F. And boom. That's the curve. The traditional shape that we wanted looks good. And it says that at the residence time there should be 0.632. So we could go here, and at the residence time of 600, 0.632. So that's good. So let me change this, though, because now this is F curve that is going here on the axis. And that's it. If you're going to submit that, then what you want to do is, let's zoom out a little bit. All right. So file, print, and one nice thing you can do for scaling is you say print everything on one sheet. So print the sheet on one page, and then it's not going to be all cut off like it was before I did that. See, no scaling is lame because then half your graph is on the next sheet of paper. But if you just scale it so that the whole sheet is on one page, then everything will turn out nice. All right, well, I hope this recording is useful. I'm going to post this online and send everybody a link. The assignment is due tomorrow as originally scheduled, so let me know if you've got any questions.